All right, welcome to day 48, MCT4Cers. We're getting there in this huge, long Chapter 5 polynomial functions chapter. We got today and the next day left. Actually, no, another day after that. Then a couple of days of review and a couple of days of tests. Well, we've still got a little ways to go, but we're almost done the lessons in this. Day 48. It's been a while. This is the biggest unit of the year by far. Let's get into it. The goal today in the 3-minute review is to simplify polynomial expressions by expanding. And of course, this 3-minute review is just a setup of what's going on for the rest of the class. But it's not that bad. Let's expand. And I like doing the second brackets first. And off we go. Multiply everything by everything in the second brackets. I'm going to collect those like terms here, those like terms right there. And then I'm going to multiply everything by everything. Two times everything. Oops, I forgot an X up there, didn't I? And then now I'm going to add down. And so the answer is no, it's not. I goofed. Minus 6x squared minus x plus 30. That looks good. Good. The whole idea, what we've been working on the last couple days, is we want to turn that into that. You know, we talked about how to divide polynomials like this by binomial factors. We talked about what the remainder was, but we're still a little bit away from being able to turn that into that because we don't know what to choose to try and divide so we can factor. So this is where we're sort of stuck right now. But let's see what number 2 is all about. The following expressions give cubic expressions of the form, and that's a cubic expression, ax cubed, bx squared, cx plus d. It says, for example, the polynomial number 1 has a is 1, b is minus 6, c is minus 1, and d is 30. There's a nice way for you to check that. Hopefully you did. State d for the polynomials below. So this is just the constant term. It wants to know what this constant term is that's kicking around on the end here. What's this thing? Well, where did that come from? That was just 2 times minus 5 times minus 3. It was all the number parts multiplied up. 2 times minus 5 times minus 3 is positive 30. So all I'd have to do is multiply minus 2 times 3 times negative 1, and I get positive 6. D must be positive 6. So in here, I got 9 times 2 is 18. D is 18. In this one, multiply them all up. D is 56. And hopefully you saw that pattern. And if you didn't, now you do. We get the last term just from multiplying all the numbers. I don't need to expand all these. All right, today, big day, the factor theorem. Yesterday we did something called the remainder theorem. This is the factor theorem. The remainder theorem from last class said that if you took a polynomial, p at x, and you divided by x minus k, the remainder is, well, it was just p at k. Right? We just substitute k in, and that's the remainder. An important extension of this is the factor theorem. If p at k is 0, that is, if the remainder is 0, that's what that's saying, the remainder is 0, then what does that mean? It means this thing that I divided by must have been a factor. That's the factor theorem, that x minus k is a factor. And as it turns out, this is a big deal. Because that's what we want to do. We want to be able to factor stuff so we can graph them. So there we go. Factor completely. So what's the idea? If we end up with a remainder of 0, and if I call that f at x, the idea is I'm going to try some stuff. And if I find that f at whatever is equal to 0, if this is true, then I have x minus 3 as a factor, and I know what to long divide. That was a big spot where we got stuck. But I got to check this out. I don't know that f at 3 is 0. I want to check it out. Well, what is it? Ooh, it might be close. It might be close. What do I got? This is 27 plus 27 minus 18 minus 8. No, there's no way that's not 0. So what can I say? X minus 3 is not a factor. Well, this kind of like, I just pulled out 3 because I wanted to try something to get us going. But now that I'm thinking about it, we might be here forever trying to check things. Right? Well, how do I know what even to try here? Well, that's where the 3-minute review came in, right? Remember, the whole idea is I'm going to factor this into three binomial expressions. I'm going to have, a factor, a number there, whatever it is, and a number there. And remember, these 3 things, when I multiply, are going to give me minus 8. So what k values do we guess? We only guess values that will divide into d. Which is the constant term, the last term. That's d right there. So in retrospect, this was a really stupid thing to try because 3 doesn't divide into 8. There's no way one of those were going to be 3 because when I multiply that up, I'm never going to get 8. I should try things like 2s and 1s and 4s, right? I'm going to try k equals, maybe 1 or negative 1 or positive and negative 2 or positive and negative 4, positive and negative 8. Well, as it turns out, as soon as I get one, I don't have to try all these. As soon as I get one of them to work, I'm golden. I'm off to the races, and we'll show you how in a second. But it does take a little bit of work, so I'm going to try, start easy. Start at f at 1, and this one doesn't work, and you're going to get pretty good at your calculator trying these values, evaluating these values, and that ends up being 1 plus 3 is 4, minus 6 minus 18. Well, it's not 0. X minus 1 is not a factor. Well, what is? Well, let's try another value. Let's try f at 2. And as it turns out, f at 2, and some of you will just go back and change the 1 to a 2 in your calculator. That's a good idea. You'll get f at 2 equals 0. So what does that mean? Therefore, x minus 2 is a factor. That means x minus 2 goes evenly into this thing. Well, what am I going to do now to find the other factors? Now I'm going to use long division. And watch the magic now. Because you got good at this the last couple of days, at least I hope you did. Use long division, multiply by x here. Subtract, be careful. The nice thing is about the factor theorem, I know it has to go evenly. I know this has to be 0. The remainder has to be 0. Otherwise, I would have goofed up my factor theorem. So I know it's got to work out. And bring down the 8, and then positive 4. And this has got to work out. Otherwise, I've goofed something up. 4 times x is 4x. 4 times minus 2 is minus 8. And there's the remainder 0. Okay, good. So what does this mean? Well, it means that that polynomial that I started with, I called it f at x. Therefore, f at x is equal to x minus 2 times x squared plus 5x plus 4. Well, this isn't factored. Excuse me. I thought we were going to have 3 brackets. Well, we will. Just keep going, right? Just keep going, because this factor is like a grade 10 trinomial, simple trinomial, numbers that multiply to get 4 and add to get 5. That's 4 and 1, right? There. Factored completely. Pretty nice. Nice. Let's go again. So what do I try? I try numbers that divide evenly into 3, right? Try f at 1 maybe. Is f at 1 equal to 0? It doesn't look like it. And do you have to write this out? No, I'm okay with you just checking it on your calculator, but I don't have a calculator handy, so I'm doing this in my head. It's not 0. So I try something else. Try f at 3 maybe. Or maybe I'll try f at minus 1. Right? F at minus 1 divides into minus 3, so maybe that'll work. And it does. One thing, a word of warning, folks, when you're using minuses and evaluating them, putting them into your polynomial functions, put brackets in there, right? So when you go -1 squared, that's -1 in brackets squared. Don't get messed up by that, okay? Be careful with your minuses. All right. That's equal to 0. So therefore, what's the factor? Well, it's x minus minus 1, or x plus 1 is a factor. And so I'm going to use long division. And then off we go into long division. 2x squared will work. Subtract. Minus 8 comes down. Remember, if I'm going too fast, you can pause the video and give it a good think about what's going on. And remember, this has got to work out, because I found that x plus 1 is a factor. This has got to work out evenly, otherwise I've goofed something up. Bring down the minus 3 here. That's minus 3. And yeah, it's going to work out. So then I can say, therefore, this expression, I'm going to say star is equal to x plus 1 times, oh, and lucky us, we've got a hard trinomial to factor here. And how you factor your hard trinomials, I don't care. But I usually use the box method. I'm going to do that over here in the margin. And I want numbers that multiply to get -6 and add to get -5, right? And it's -6 and 1. -6 and 1 works. So I put -6x here and -1x there, and I factor. That's an x there, minus 3 there. Over here is 2x. Over here is -1, and there are my factors. So this part factors further. However you like to factor, it doesn't matter. You don't have to use the box method. You have to use the sum method. And there, factored fully. Nice. Nice again. Oh, well, what's the big whoop? What's the big whoop about the factor theorem? So, well, that was pretty cool that we were able to factor stuff that we weren't able to factor before. But once we can factor, we can graph a function and know endless things about the behavior of function. That's why we're so hung up about the graphs. Is now that we can factor this, you know, I can write this in factored form. This is exactly the same one that I just did, right? I know that this is degree 3. It starts low and ends high because a leading coefficient is positive. And now I know the x-intercepts, right? The x-intercepts are x equals -1, x equals 1/2. And if you have trouble seeing that gives me a root of 1/2, I'll tell you that in a second. And then x is 3. Essentially, we're looking about what makes this bracket 0. So if you can't see that this is 1/2, well, set it equal to 0, and then solve that little tiny equation that goes over that side, and then divide by 2. There's your half. There's that x-intercept. And then I can, I'll graph this. There's -1. Where's a half? A half is over here somewhere. Say that's a half. 3 is over there. And starts low and ends high. Starts low, ends high. Yeah, I know. I don't know how far to go up or how far to go over. And we're gonna I goofed something up. Let me pause the video, see if I can find my mistake, because I just saw something. I saw the y-intercept is -3. It's supposed to be down here. So this graph should be going through -3. And you maybe saw the mistake I made somewhere, but you didn't tell me, did you? Yeah, thanks for that. Let me see if I can find my mistake. I'll pause the video. All right, I found my mistake. It was when I was factoring. When I was factoring, I wrote down -6x and -1x, but it should have been -6x and +1x, and maybe you saw that, and that makes that a positive, which makes this a positive, which makes this a positive, so fix your notes, which makes this a positive, and that makes that negative a half. So I'm going to erase my graph because it was goofed up and fix it. I'm going to fix it now. So -1 is over here somewhere, -1. Negative a half is the second root. And then +3 is going to be out here somewhere. And we don't really care too much for the scale. Starts low and ends high, all slash roots. Degree 3. And now, yes, nicely, I can find my y-intercept when x is 0, y is -3, and there's that point right there. And so the factor theorem allows us to come up with these graphs. Once I know the graphs, I can find the roots, I can find the y-intercept, I can find when the graph is increasing and when it's decreasing. I can talk about things like relative minimums and maximums. I could use the TI-83 if I wanted to find them, but I could guess. It looks like it's, the relative maximum's about there, and if I use my scale, I could even estimate that. Once I know the graph, I know endless things about the behavior of the function. And as we saw before, we've used these polynomial functions to model stuff in real life. Okay, that is the factor theorem, folks. Make on your homework today, make wise choices and stay classy.